Have you ever gotten the feeling reality might be thinner than you thought, like the wallpaper of existence might be a hint of something far stranger behind it? If so, you're not alone. In late 2024, a small box of superconducting metal called Willow forced the physics world to ask, what if our universe is not the whole story? Then came the benchmark that lit the media on fire. Willow completed a specially designed quantum sampling task in under 5 minutes, a calculation that Google said would take the fastest classical supercomputers roughly 10 septillion years to finish. That's 10 followed by 25 zeros, a number so large it makes human history look like a blink. Reporters called it mind-bending. Scientists called it a milestone. Investors called it exciting. Quantum computing is weird because it uses qubits, not just zeros and ones, but superpositions of both at once. That verbal shorthand goes back to pioneers like David Deutsch. But a marketing-friendly metaphor is not the same thing as experimental proof of parallel universes. Still, the stakes felt enormous. If a lab experiment could be reasonably interpreted as evidence for the multiverse, then certain grand theories, string theory among them, which rely heavily on mathematical universes and landscapes, would face a new litmus test. Some leading figures admitted the result forces hard questions about how theory and experiment must now talk to each other. The public sensed a narrative: a machine in California had just poked a hole in centuries of philosophical patience. Whether that hole is real, or simply a crack in our storytelling, remains the debate's battleground. Why does that matter? Because building a large quantum computer is not simply adding qubits. Each qubit introduces more ways for errors to creep in. Willow's claim is that with careful architecture and error mitigation, adding qubits can, counterintuitively, produce clearer, more reliable computations for certain tasks. That's why researchers called this breaking through a long-standing barrier in error correction. Practical quantum advantage starts with precisely this kind of progress. Yet, as many researchers immediately emphasized, the task Willow solved is a benchmark chosen to expose quantum advantage. Benchmarks are vital, they measure progress, but they are not the same as demonstrating broad, general-purpose quantum advantage across useful applications like breaking encryption, simulating complex chemistry, or solving everyday optimization problems. In short, Willow is huge for the field, but it's not a magic wand. So where does the multiverse fit in? The multiverse interpretation offers a way to picture why quantum systems scale in power. Each quantum possibility is a branch, and computation is interference of branches. Nevin's blog referenced this picture, arguing that Willow's performance is consistent with an interpretation where many possibilities are physically relevant. Critics hit back fast and hard. Leading theorists and skeptics argued that invoking parallel universes to explain a benchmark is unnecessary and not experimentally justified. What this debate revealed is a deeper cultural fissure in modern physics. On one side, the builders, engineers, and experimenters who produce reliable devices and incremental truths. On the other, the theorists who want clear, reproducible experiments that address foundational questions. Willow sits in the middle, an engineered object that provokes philosophical speculation. Some senior physicists, quoted in op-eds and conversations after Willow, suggested we might need to rethink decades of work. Not because one chip disproves string theory, but because data that bears on ontology compels us to demand empirical constraints. If quantum computing begins providing such constraints, then the theoretical playground will finally have referees. Importantly, no leading scientist has declared string theory dead. What happened instead is that the Willow episode intensified calls for empiricism, new data, new tests, fewer philosophical free passes. That's healthy. Science advances when bold ideas meet stubborn facts. We end where we began, with a question that feels like science fiction but is now pressingly real. Is reality information first, patterns and computation first, or is some deeper geometric/stringy structure the bedrock? Willow does not answer that. But it shows how laboratory progress can push philosophical questions into the empirical realm. That's a revolution. Right now, we stand at the edge of an experiment that could change not just computing, but our cosmic self-image. Willow is not a verdict. It's a question thrown into the world in metal and superconducting wire. It asks, how bold are we prepared to be with our hypotheses? How willing are we to let machines test our grandest ideas? So subscribe, because this story is just beginning. In the months and years ahead, groups around the world will design new experiments and new chips. They will test, argue, and, ultimately, let reality decide.